Welcome to Lumora, where science meets mystery. Tonight, we unravel the enigma of 3 Atlas, a visitor from beyond the stars that vanished just as the world began to understand what it truly was. In late October 2025, 3I Atlas, the third known interstellar object ever detected, slipped behind the sun. For 2 long weeks, it was hidden from every telescope on Earth, unreachable and unseen. Astronomers called this period the solar blackout, but to many it felt like something far more deliberate. Because before disappearing, 3I Atlas had begun to behave in ways no natural comet ever had. At first, scientists classified it as a comet, icy, tumbling, and ordinary. But its chemistry broke the mold. Instruments from NASA, ESA, and private observatories picked up a ratio of carbon dioxide to water, unlike anything seen before. Nearly 8 parts CO2 for every 1 part H2O. It wasn't a statistical fluke or an error. Multiple observatories confirmed the same result. For the scientific community, that ratio screamed anomaly. For others, it whispered something even stranger, intention. And that wasn't the only mystery. The comet's light didn't brighten smoothly as it neared the sun. Instead, it pulsed in sharp step-like bursts, as if some unseen mechanism were controlling the energy release. Bright one day, flat the next, bright again, each jump clean, almost digital. As 3C Atlas disappeared into the solar glare, the world held its breath. Telescopes went dark, satellites recalibrated, and speculation surged. Was this the signature of a frozen relic from another star, shaped by alien chemistry? Or could it be something designed, a probe, a vessel, a messenger cloaked in ice? No one could know, because at that exact moment, every eye on Earth was blind. This blackout wasn't just an observational inconvenience, it was a cosmic silence. For the next 3 weeks, from late October through early November, 3/Atlas would pass through a region of the sky. A sky too close to the sun for any ground-based instrument to track. Whatever happened during that window, fragmentation, acceleration, even transformation, would unfold unseen. When it finally emerged again, the question wouldn't be just what 3I Atlas was, but whether it had changed. The story of 3I Atlas began quietly, months before the world even knew its name. In mid-2025, deep sky survey telescopes were scanning the southern heavens when an unusual point of light appeared. Faint, fast, and moving too quickly to belong to any known family of comets. It wasn't until a team at the Atlas Observatory cross-checked the data that the object revealed its true nature. Its orbit was hyperbolic, not bound to the sun, arriving from the direction of Sagittarius and destined to leave again forever. That one detail changed everything. This was no ordinary wanderer from the Oort cloud. It was an interstellar visitor, only the third ever found, after Oumuamua in 2017 and Borisov in 2019. But even among that rare company, 3I Atlas stood apart. Its speed, over 58 kilometers per second, made it one of the fastest natural objects ever tracked. And early photometric readings hinted at something massive. Models suggested a nucleus between 2 and 5 kilometers wide, possibly the largest interstellar body ever detected. Inside, observatories from Hawaii to Chile, nights blurred into one another. Every 24 hours, data poured in. Spectra, light curves, positional plots, each one raising new questions. Could this truly be interstellar? Or was it a hyperactive long-period comet from the farthest edges of our own system? The numbers answered. Interstellar, without doubt. Its incoming velocity was simply too high for any solar-bound origin. The team led by Dr. Heinrich debated each anomaly in real time, aware that one error in classification could ripple through the entire field. Emails flew between ESA, NASA, and independent observatories. What unsettled everyone wasn't just its origin, but its timing. The object's perihelion, the moment it would pass closest to the sun, was set for late October, placing it directly behind the sun from Earth's point of view. That meant a total observation blackout during its most critical phase. Still, the discovery electrified the scientific community. Here was a piece of another star system, crossing our path for the briefest moment before vanishing again into the dark. Every night brought new urgency, every detection a fragment of a larger cosmic puzzle. And as its brightness grew, so did the sense that something extraordinary was unfolding, something the world might never fully comprehend. By mid-October 2025, the countdown had begun. Astronomers around the world prepared for what they called the solar conjunction blackout, a period when 3I Atlas would pass behind the sun, completely out of Earth's line of sight. Telescopes from Chile to Hawaii began shutting down observation schedules, knowing that for nearly 3 weeks the object would become invisible. This wasn't just an inconvenience, it was a scientific void. During this critical window, the comet would reach perihelion, the point of maximum solar heating, when most comets erupt into spectacular jets, shedding material and revealing their secrets. But this time, no one on Earth would witness it. Any sudden flare, fragmentation, or trajectory shift would unfold in silence beyond our reach. Only a few robotic eyes had a chance. Orbiters around Mars, ESA's Trace Gas Orbiter and NASA's MAVEN, were positioned just far enough from the sun's glare to maintain a partial view. For a brief moment, they became humanity's only observers. Their instruments, designed for planetary atmospheres, were hastily reprogrammed to track the interstellar intruder. Engineers at ESA called it a cosmic gamble, and it worked. On October 3rd, the Mars Express and TGO captured fleeting images, a bright, asymmetric coma trailing a thin, teardrop-shaped dust plume. It wasn't like the diffuse, fan-shaped tails typical of ordinary comets. This one looked contained, almost structured, sharp edges where none should exist. Spectrometers confirmed elevated levels of carbon dioxide and faint traces of hydrocarbons, reinforcing the earlier readings. Something about 3I Atlas was resisting explanation. As Earth's telescopes went dark, Mars became our proxy. Every few hours, packets of data arrived through the deep space network, delayed by millions of kilometers. Each batch carried whispers from the unseen side of the sun, changes in brightness, subtle variations in trajectory, and new details of the comet's evolving shape. Then, on October 21st, the signal faded. The geometry between Mars, the Sun, and 3 Atlas finally closed. Humanity was blind once more. In those silent weeks, speculation replaced observation. Some scientists argued that the object's smooth spherical shape hinted at a natural but rare formation, perhaps a frozen remnant of a carbon-rich system. Others whispered of something designed, built to harness the sun's energy before continuing its journey. And as November approached, one question echoed through every observatory control room. What would 3I Atlas look like when it came back into view? When 3I Atlas reappeared, the data stunned even the most cautious scientists. Spectrographs tuned to its coma, the glowing cloud of gas and dust surrounding its nucleus, reported chemical ratios that broke every rule in the book. Instead of water vapor dominating the readings, as is typical for nearly every comet ever studied, carbon dioxide reigned supreme. The ratio? Almost 8-to-1. It was not an error, nor a miscalibration. The same pattern emerged from multiple instruments: the James Webb Space Telescope, the Mars Orbiter's infrared sensors, and ESA's VLT arrays all confirmed it. Statistically, the anomaly stood 6 standard deviations above anything known. In the archives of cometary science, only one other case, C2016R2, had come close. But even that pale comparison showed nothing this extreme, this sustained. The composition alone was shocking, but there was more. Within the coma, researchers detected complex organics, carbon chains, hydrocarbons, and nitrogen-bearing molecules, usually scarce in standard solar system comets. Their abundance hinted at a formation far beyond our familiar chemistry, perhaps in a cold, carbon-rich disk orbiting another star. Some planetary chemists proposed that interstellar radiation could have reprocessed the surface over eons, forming a crust that trapped water beneath and left carbon dioxide exposed. Others quietly wondered if such precision could occur naturally at all. Then came the images. The Hubble Space Telescope's first clear capture of 3I Atlas shocked the astronomy community. Instead of a rough, lumpy body like every other known comet, this object appeared remarkably smooth, almost perfectly spherical, its surface unbroken by the deep pits or jagged scars typical of ancient ice. A comet like this simply shouldn't exist. Even more puzzling was the shape of the coma itself. High-resolution interferometry revealed an elongated teardrop structure, as if the dust were being channeled or constrained rather than freely expanding. The edges looked sharply defined, almost symmetrical, defying the chaotic spread that solar wind should produce. Models failed to replicate the formation under normal physics. Every image seemed to challenge the definition of what a comet was supposed to be. Could it be rotating in a way that directed its jets into a single plume? Or was there an unseen magnetic field shaping the dust? Theories multiplied, but none fit perfectly. For planetary scientists, it was thrilling. For everyone else, it was unsettling. Something about 3I Atlas felt engineered, not in its chemistry alone, but in its geometry, its precision, and the eerie sense of control behind every anomaly. Whatever this was, it was unlike anything the solar system had ever seen. By late November, the long blackout was over. 3I Atlas had emerged from behind the sun, and every telescope on Earth turned toward it. From Chile's Atacama Desert to Hawaii's Mauna Kea, instruments realigned, software recalibrated, and observation schedules rewritten overnight. The race to capture the first post-conjunction images had begun. At the European Southern Observatory, the Very Large Telescope prepared a high-cadence imaging campaign. Using interferometry, astronomers combined the light from multiple 8-meter mirrors, achieving a level of detail never before applied to an interstellar object. Their goal was simple: to see if 3I Atlas had changed while it was hidden. Had its surface fractured? Had the smooth nucleus remained intact? Or had something new appeared? Jets, fragments, even structural realignment. Meanwhile, across millions of kilometers, ESA's JUICE spacecraft, en route to Jupiter, entered its own observation window. Its ultraviolet and infrared spectrometers, designed for faint, fast-moving targets, began scanning the interstellar visitor from a completely different angle. With JUICE's unique vantage, scientists hoped to confirm or challenge the chemical anomalies seen before the blackout, especially the bizarre CO2 dominance in the complex organic signatures. Back on Earth, global networks coordinated around the clock. The VLT in Chile, Gemini in Hawaii, and the Subaru telescope in Japan worked in unison, forming what the press began calling the Atlas Watch. Every observatory focused on 3 key indicators: brightness fluctuations, rotational stability, and trajectory drift. Brightness would reveal whether the step-like surges seen before perihelion were repeating. Rotation could confirm if the object's peculiar 17.3-hour spin remained stable, or if it had shifted, suggesting internal change. And trajectory drift would tell whether non-gravitational forces, such as jets or something else, were subtly altering its course. The data began to arrive, and with it, more questions than answers. Some frames showed faint plumes emerging from new locations, while others hinted at the same sharp-edge coma shape as before. No visible fragmentation, no dramatic breakup. Yet the light curve told a different story. Small, precise jumps in brightness returned, almost rhythmic this time, as if following a hidden sequence. For the scientific community, it was exhilarating. For the skeptics, it was vindication. Something about 3I Atlas seemed too consistent, too measured, to be a mere coincidence of natural physics. The next few weeks would determine everything. Each observation, each pixel of data carried the potential to answer or deepen the question that now gripped the world. Was this object a natural wanderer from another star system? Or had humanity just encountered something built, something purposeful, drifting through our solar neighborhood? As December unfolded, the debate over 3I Atlas reached its peak. The data was no longer just numbers, it had become a story, and that story divided the scientific world. On one side stood the planetary physicists, who clung to the idea that nature, no matter how strange, could still surprise us. They argued that the carbon dioxide dominance might simply point to a birthplace rich in frozen volatiles, an exotic nursery orbiting a distant red star, where temperatures remained cold enough for carbon dioxide to dominate and water to hide beneath the crust. Over millions of years of cosmic radiation, the surface could have hardened into a mirror-smooth shell, while internal jets occasionally broke through, creating the step-like bursts of light that puzzled Earth's astronomers. But others refused to accept coincidence as explanation. Dr. Elena Vergara, a spectroscopist known for challenging consensus, pointed to the near-perfect symmetry of the nucleus, its unusual brightness rhythm, and its convenient trajectory, threading a narrow path between Mars and Jupiter before disappearing behind the Sun at the exact moment of maximum activity. "It's too precise," she said, "too deliberate." Her team suggested a different hypothesis, one that bordered on heresy. What if the brightness jumps weren't random jets, but signals? Controlled energy emissions timed to some internal mechanism? What if the smooth surface wasn't the product of time, but design, a shell engineered to protect something within? The world's observatories continued to feed data into shared archives, comparing every deviation, every rotation, every flicker. The final tests were underway. Would 3I's Atlas fade naturally as expected, or sustain its strange rhythm? Would its course remain stable, or drift as if propelled by something unseen? Every prediction now hinged on a handful of measurements. The light curve, the rotation pattern, the chemical ratios, all of it would decide whether 3I Atlas was the most extraordinary comet ever discovered, or the first evidence of something built. As the last frames of the observation campaign arrived, one truth became clear. Whatever 3I Atlas truly was, it had changed how we look at the universe. Because sometimes, the line between the natural and the designed isn't drawn by proof. It's drawn by the questions that refuse to fade. And for 3I Atlas, those questions have only just begun.